This C# script has been developed to demonstrate how big O notation can be used to represent the scaling and time it would take to run an array. This script was adapted from a YouTube video posted by Scott Duffy, and so that was accessed on January 10th for this video. This is the link to that video if you want to watch his version of the script. And so what we're looking at is the runtime of big O notation as it represents, we're going to look at O1, ON squared, and the log of n, which is essentially a simple binary search algorithm. We're going to do all of this evaluation using big O, looking at the time. In this case, we're just looking at steps. We're not really measuring time in milliseconds of the algorithms. We're just trying to demonstrate how many steps it would take to complete a specific compute operation given a different version of an algorithm. And so we look at O1 first, and what we've got here is a simple array. We call it test array, and we populate it with 20,000 elements. So let's come look at the O1 notation. And all we're doing with O1 is we have a variable here called loop count that we initialize to 0. And we assign the subscript 0, or the first element within the array, as the integer value 1 here. So the array above, the test array, gets passed into this method, and we rename it inArray. And we just simply, although we're incrementing this loop count variable by 1, that's all we do. So this algorithm, no matter what the size of the array would be, is going to execute within the same amount of time. So O1 is just a single chunk of information, a single execution here, in this case, this algorithm, in a single amount of time, no matter the size of the data. If we move on to ON notation, we initialize the loop count variable to 0 again. In this case, what we're going to do is we bring in the test array, and it's available to us in this method. We're going to run a for loop, and we're going to iterate through that array the number of times that it takes to exhaust to the length of the array, which we know that the array is 20,000 elements long. And each time we iterate through the array, we're going to increment the loop count variable by 1, and at the end print out the number of steps it took to execute this algorithm. So this algorithm with ON demonstrates more expense than O1. So that's what we're demonstrating here. So here we're getting even more expensive of an algorithm. It would perhaps take more time to execute. So in this case, we're showing O of n squared, where n squared in this case is demonstrated by a loop within a loop. So we're bringing that array of 20,000 elements in, and we have our counter variable available to us in this method, just the same as before. And so each time we go through an element within the array, we then iterate an inner loop within that. And so essentially we're executing this loop n squared, and we would get the value of 400 million, where 20,000 squared is 400 million. And each time we iterate through the loop within the loop, we increment the loop count variable by 1. And when that completes, we print that out through the console. Here we have the log of n, where we demonstrate essentially a simple binary search algorithm. So this one, although has a lot of steps, what's interesting to get out of this is that when we have well-known algorithms that have proven to be efficient that we could use within our code. You can see this demonstrated here where we have an array that is 20,000 elements. And in binary search, what we do is we have our counter variable here. We're going to generate this random number. We get the length of the array, and what we do is we define the upper and lower bounds of the array, and then we locate the middle of the array. So in binary search, it always cuts the list of values in half, and then takes half of that and makes it smaller in half yet again, and continues to exhaust that until it can no longer divide the list in two. So that's what's happening here, where we have a while loop that gets the array and begins to continue to identify the upper and lower bounds of the array and identify the middle and break it in half. And then as it does that, each time it goes through the loop, we increment the count by 1 and keep track of how many times that this operation will take until the array is exhausted. And so although there's a lot going on in this algorithm, it will prove to be more efficient than, say, the n squared. So let's demonstrate this. If we just click the execute in debug mode, we can see O1 completed in one step. So it did not have a very expensive operation. It's designed to continuously execute in the same amount of time each time, no matter how large the data. We completed ON in 20,000 steps, so it was a lot more expensive than O1 because it had to run, the algorithm had to execute 20,000 times with a loop. With ON squared, it was very expensive, where the loop executed within another loop, so a nested loop, which came with n squared at 400 million, which would be 20,000 squared. And then finally, this log_n, essentially demonstrating a simple binary search algorithm, completed in only 13 steps. So ON, as you can see demonstrated here in the C# code, is an important conceptual understanding when trying to understand the scaling of algorithms as you write them in your programs and solve problems.